Okay, so we want to find a quadratic kernel for the problem of vertex cover. What this means is that once I run the algorithm, the kernelization algorithm, I should be able to get an instance of the graph having vertices, at most a quadratic function of k, or the parameter. So basically, if I go back to the definition of kernelization or simply kernel is a parameterized problem Q of a parameterized problem Q is an algorithm A that computes a new instance I dash k dash, and the size is bounded by a function of g, and I want this function g to be a quadratic in k. Okay, of course computable. So I have, now you may ask that why can't I just keep repeating the use of this to get the actual answer, to keep reducing to a very small instance and then just compute the answer right away. Now the thing is, the algorithm A only works on certain types of instances, and I will, so those instances must have, so we have some reduction rules over here, and if these reduction rules apply, only then can you use the algorithm A. So the first reduction rule for this kernelization algorithm A is that if you have an isolated vertex V, then we delete the isolated vertex V from the graph G, and it's pretty obvious. So an isolated vertex does not contribute towards vertex cover, because if you remove that, you don't remove any edge, basically. So I can remove an isolated vertex, and also since I'm not adding that vertex to the vertex cover, I don't need to decrement my value of k, because I still have k vertices left to choose. So if I apply this reduction rule, I get a new instance which will have all the isolated vertices removed, and the value of k will still remain same, that since I did not include any of those isolated vertices in vertex cover. Now the second reduction rule is so when I have a vertex with degree more than or equal to k plus 1, what it means is that if I don't choose that particular vertex, I will have to choose all the other vertices, that is all the other k plus 1 vertices. But since my budget is only k, I can only choose k vertices. I then have to choose the vertex which has a degree more than equal to k plus 1. So then I apply this rule to get a new graph having that particular vertex removed, and since I add that vertex in my vertex cover, I also decrement the value of k, and I keep repeatedly applying these two rules until I get a new graph on which these two rules cannot be applied. And if I have a new graph on which these two rules cannot be applied, I can say something about that new graph. Now just assume that we have a vertex cover for that new graph. Let it be a set S. Okay, and each of the vertices in the set S will have a degree at most k, because if the degree was greater than k, then I would have removed that vertex using rule 2. Okay, and also there are not going to be any isolated vertices. Now in order to get the maximum number of, now each of the vertex in S is going to have a degree k, and since S is a vertex cover, we know that it contains at most k vertices. So then Now suppose if I want to find a graph having most number of vertices for which there exists a vertex cover of size k and the degree of each vertex is at most k. I would rather use this argument given in the book. So the number of vertices in graph G minus S is less than equal to k times the size of S. But number of vertices in the graph G minus S is basically number of vertices in the graph G minus the number of vertices in set S. So if I take S on the right side, it becomes k plus 1 times S. So the number of vertices is less than equal to k plus 1 times size of S, which is again k, since S is a vertex cover of size at most k. What this means is the number of vertices in graph G. Now this is actually pretty obvious. So you can think of it as a collection of stars like this. I just want to increase the number of vertices as much as possible. This is 1, 2 and so on, and I will have k stars, and the degree of each is also k, so therefore each star will have k vertices surrounding, and so the total number of vertices is k into k plus 1. But anyway, so the graph G will have at most k into k plus 1 vertices. Now if the graph G has more than that number of vertices, then I can straight away say that it's not going to have a vertex cover of size k. Yeah, also you can say that the number of edges is k square at most. But if the graph has less than k into k plus 1 number of vertices, I cannot really say that the graph still has a vertex cover, because it's not necessary for the vertex cover to be present. For instance, if my k is 2, yeah, it's not necessary. So what I then have to do is consider each combination of the vertices present here. So that will be 2 to the power k number of subsets, and for each of the combination of vertices I will have to see whether that is a vertex cover or not. And okay, now this you may say is a very naive algorithm, but it doesn't matter, since the time taken will be still a function of k. It will be, if each subset takes some c amount of time for it to be computed, the total time taken will be something like this. And application of these two rules until we can find a graph for which these two rules cannot be applied. Now this whole process also takes some polynomial time, and it will be a polynomial in the instance size, that is g here. So the total time will be 2k times c plus mod the size of the graph g, and yeah, so we have an FTP algorithm with the time at most this, where f is 2 to the power k times c. Oh, 1 second. So this, let me explain. So this is less than equal to 2 to the power k times c times mod g, and since g was my instance, it is basically equal to f of k times my instance size. And yeah, it could be some polynomial in g as well. So whole of this time, whole of this process could have taken, whole of these application of these rules could have taken some polynomial time. So I also have a constant c dash. But anyways, I have an FTP, and this function f is so this instance size is bounded by some quadratic in k. In this case it is k into k plus 1, and that's why I say that my kernel is a quadratic kernel.